In this video, I've prepared some short questions that can all be answered by inspection of the TXY or the PXY diagram. And this will be good use in practicing using these TXY, PXY diagrams to solve phase equilibrium questions that involve multiple condensable components. The first one is, what is the boiling point of pure toluene at 1 atmosphere? So the way I'll do this is I will show you the TXY and the PXY diagrams. I'll repeat the question and I'll pause for a few seconds, allowing you to pause the video and to answer what you would say. And then I will give you the answer after that. So once again, what is the boiling point of pure toluene at 1 atmosphere? Remember that the terminology of boiling point is for a pure component. And indeed, I'm talking about pure toluene at 1 atmosphere. Because I'm talking about pressures being specified and temperature can vary, I'm going to want to look at the TXY diagram where pressure is constant. Thankfully, I do have the pressure is 1 atmosphere for this particular diagram. The question also asked me about toluene, but rather mole fraction of benzene is listed on the x-axis. Remember, however, that the component of the composition of the other component is simply 1 minus the mole fraction of the component that's shown for a binary mixture. Something else that needs to be said, or we should review also, the caption TXY, PXY diagrams for benzene toluene system. So any good TXY or PXY diagram should tell you the two components that they're talking about, and it should also tell you the set value of the other variable. So for the PXY diagram, I have a set temperature. For the TXY diagram, I have a set pressure. So looking at pure toluene is going to correspond to 0% benzene. That's an equivalent statement. When the system has 0% benzene, and if it only contains benzene and toluene, then the other 100% must be toluene. And to get the pure boiling point, I simply have to look at where phase equilibrium occurs. Now notice that in the TXY diagram, the dew point curve and the bubble point curve come together, which matches the intuition from a previous video that I said that for pure components, vaporization and condensation occur at the same temperature, which we just call the boiling point. For all other mixtures, these temperatures are different. So looking at this diagram then, I can simply read the temperature off that diagram for pure toluene, and I can say that the answer is about 110 degrees Celsius. This is also something that you can verify in the back of the book by looking at table B1. And I might not have the precision that the back of the book does. So if you had a choice of whether or not to use a TXY diagram or a table, then I would definitely use the table because you have more significant figures there, and there's bound to be some error when you're reading these diagrams. So I can't tell if this is 110.2 or 110.1. The closest I can say is 110. Okay, let's move on. Number 2 says a mixture of 20% benzene, 80% toluene is heated to 80 degrees C at 1 atmosphere. Is the system in equilibrium? So here I have both temperature and pressure specified. I also have a composition specified. So therefore I need to determine whether or not the system is in equilibrium. So the way I can do that is by looking at the diagram. I can plot the coordinates 80C in 1 atmosphere, and if those coordinates lie within the two-phase region, then I'll know that I am in equilibrium. So I'm not going to use the PXY diagram for this because the PXY diagram, once again, is only for T is equal to 100 degrees C, and I want the situation to be 85 C. However, 1 atmosphere does indeed match 1 atmosphere on the diagram. So I'm going to use the TXY diagram and say that at 1 atmosphere and 85 C, correct, I'm going to want to look at 20% benzene. So 20% benzene is there. The coordinates are right here. So this point does not lie within the two-phase region. This point is firmly within the liquid region. So the answer to this question is no. The system is all liquid at this point. Okay, moving on to number 3. For the same system as number 2, it's heated to the bubble point. What is the composition of the first vapor that forms? So heating a mixture of a certain composition means that we are rising vertically upward on this graph. So as temperature increases, the point at which I'm at also continues to increase. And the bubble point is going to be the point that I first touch this bubble point line. Now, the composition of the vapor that forms, in order to get that, I need to draw myself a tie line. And then I can look at the composition of the vapor on this diagram. So remember, the composition of the vapor is the one that is on the dew point curve, or I like to think of it as the one that is closest to the vapor. Well, once again, if you get confused about which one that is, or if you don't like to memorize things, you can always look at it as which component is more volatile. And by looking at the pure component boiling point, so we already answered for toluene. For benzene, it would be about 80 degrees Celsius. So benzene has the lower boiling point, and therefore benzene is going to be more volatile. Therefore, benzene is going to want to vaporize more easily. Therefore, the composition of benzene in the vapor phase should be greater than the composition in the liquid phase. I'm going to write that because that is an important bit of intuition that you can use so that you don't have to memorize things. Okay, so reading that composition off the diagram, then I would say about 41%. The first bubble that forms is 41% benzene, and then the balance, remember these have to add up to 100%, 59% toluene. The remaining liquid is still the same original composition. It's still 20% benzene, 80% toluene. And that is because vaporizing one bubble doesn't really change the composition very much. If I continue to heat, that's actually going into number 4. That says the same system is heated slowly. At what temperature does the last remaining drop of liquid evaporate? What is the composition of that drop? So we're continuing to move upwards. And if I were at 105 degrees, for example, remember I'd still have the tie line. The composition of my liquid and vapor phases could then be found. This particular question asks me at what temperature does the last remaining drop of liquid evaporate? This is asking me what is the dew point? What is the dew point? Okay, so I just continue to rise until I reach equilibrium again. And the composition of the last remaining drop of liquid, drawing my tie line over, would be roughly 8% benzene. Composition of last drop is about 8% benzene, and the corresponding 92% would then be toluene. And the temperature at which that occurs, I'm going to call about 107 C. Okay. Vapor mixture of 40% benzene, 60% toluene is cooled slowly. So let's erase now everything. See if you can get this one on your own. I'm going to pause again. 40% benzene, 60% toluene cooled slowly. At what temperature does the first drop of liquid form? So 40% benzene, 60% toluene is along this line. Once again, I'm looking for the dew point temperature, which is right there. I have to assume that this is at 1 atmosphere. This is bad question writing practice. If you're asking this question, remember you have to specify what the pressure is. So let's say assuming 1 atmosphere. Because the actual answer to this question is it's impossible to determine without a pressure. But the fact that I have given you the TXY diagram at this pressure kind of implies that that was what was meant. Okay, so the temperature again is 102 degrees C. Same system is cooled until the components of the liquid is 30% benzene. What temperature does this occur? So I'm kind of asking you the same question just in various different ways. The composition of the liquid being 30% benzene corresponds to the point at which, this is a 30% benzene line, at which my liquid composition is here. And drawing a tie line over, I could also get what the composition of the vapor is. So the temperature at which this occurs is about 98 degrees C. And the composition of the vapor at this point is about 51%. And corresponding 49% is toluene. For number 6, what percent of the initial vapor has condensed? So in order to do this problem, I'm going to have to do a material balance. This is a slightly different question. What percent of the initial vapor has condensed? So in order to do that, I'm going to need to know what the initial was and what the final compositions are. So I am going to need to assume a basis. I don't know how large the system is. It doesn't matter how large the system is. Assume a basis of 100 moles. And my material balances now are going to be of the form final is equal to initial rather than in is equal to out. So initially, what I have 100 moles at 30% benzene and 70% toluene. So that is going to correspond to 30 moles when I take into account my basis, 30 moles benzene, 70 moles toluene. That is my initial. Final, I'm going to have a certain amount of liquid and a certain amount of vapor, which I don't necessarily know what those are yet. I have liquid at, let's see, the components of the liquid is 30% benzene. Oh, wait a minute. I made a mistake. 40% is the initial. So I had to go back to number 5 for the initial. 40% benzene, 60 mole percent benzene. Yes. So 60 moles of benzene, and I think I had this. No, 40 moles. I'm all over the place. 40 moles benzene, 60 moles toluene. Okay, that makes more sense. Liquid is at 30% benzene, and my vapor is at 51% benzene. All right, so I can write material balances now. I have 2 components, benzene, toluene, so that means I have 2 material balances. And once again, instead of writing both component material balances, I'm going to substitute the overall for one of them. So the overall balance is going to be equal to the moles of vapor plus the moles of liquid is equal to 100. Or the benzene balance is going to be 40, because that's how much I said that I had initially. I wrote this backwards. If I want to be consistent, I should have wrote 100 is equal to V plus L. 40 is equal to 0.30 times L plus 0.51 times V. And now this is a system of 2 equations, 2 unknowns that I can solve. So I would probably substitute in for L, would look to be easiest. So I'd have 40 is equal to 0.30 times 100 minus V plus 0.51 times V. Distribute out, 40 is equal to 30 minus 0.30 V plus 0.51 V. And doing this calculation is 15 is equal to 0.21 V. And finally, calculating for V, we grab my calculator, 15 divided by 0.21 is 71.4 moles. Therefore, my liquid must be the other 28.6 moles. So again, what percent of the initial vapor has condensed? Percent of the initial vapor that has condensed is going to be L divided by 100, or equal to 28.6% of initial vapor condensed. Whoa, scratch that. Okay, I don't know what I was doing there. 40 minus 30 is 10, not 15. Must have been looking at the wrong thing there. I'm going to have to recalculate this stuff. So 10 divided by 0.21 is 47.6. And 100 minus that is 52.4. So 52.4 divided by 100 is 52.4% of initial vapor condensed. That makes much more sense. So hopefully this video gives you some more practice and intuition about how to use these TXY diagrams. Notice that I did all these example problems for the TXY, but you could use the same logic to figure out what the pressure is. And the PXY works exactly the same. The only difference is the vapor and the liquid are switched and temperature is on the y-axis instead. That'll be all for this video.